Good evening. My name is Deniss Zerkalijs, and this is my presentation for the fabrication and analysis of porous gelatin with beta-tricalcium phosphate scaffolds for the BME 405 tissue engineering module in Galway. This study's objective is to manufacture scaffolds of gelatin and gelatin with beta-TCP and to determine their suitability as bone tissue engineering materials. It was expected that the integration of beta-TCP nanocomposite to a gelatin scaffold will produce a composite scaffold that is structurally and physiochemically suitable for bone tissue engineering applications. 3 gelatin control scaffolds and 3 more gelatin with beta-TCP porous and GTA cross-link scaffolds were fabricated as follows. Gelatin was obtained from porcine skin from Sigma and was used to prepare 2 distinct solutions suspended in 100 ml of phosphate buffered saline, or PBS for short. Beta-TCP was also obtained from Sigma and was diluted into one of the 2 solutions to create 100 ml of 5% gelatin and 10% beta-TCP suspension. The other solution was left as a control. 80 ml of each solution was then put into a tray, creating a thickness of 5 mm for each scaffold, and then freeze-dried for 26 hours. To assess the scaffolds, their dimensions were taken and then were subjected to uniaxial compression testing under wet conditions in PBS. Afterwards, their swelling ratio was evaluated. They were then subjected to 7 days of degradation testing under physiological conditions and were weighed again to determine the degradation rate. The scaffolds then had their porosity and morphology assessed using scanning electron microscopy and ImageJ software. To analyze cell viability and proliferation on both gelatin and gelatin with beta-TCP scaffolds, they were seeded with MC3T3E1 pre-osteoblast cells with a seeding density of 10 million cells per scaffold. After a 7-day culture period, a Huesh DNA assay was performed to determine the density and therefore the viability of the seeded cells through the recording of their fluorescence. Following ImageJ analysis, it was found that the scaffolds with beta-TCP had a much higher porosity than the control scaffolds, which is shown in figures 2 to 5. Beta-TCP scaffolds had an average porosity of approximately 50%, whereas the porosity of standalone gelatin scaffolds was lower than 5% for each case. Figure 6 presents the swelling and degradation rate of both scaffolds. Gelatin scaffolds with infused beta-TCP show a high result in both cases compared to a pristine scaffold. These results can be controlled with ratios of chemicals during fabrication to simulate the physiological conditions. Figure 7 shows the stress versus strain curve used to predict the compressibility of the material and calculate the compressive modules, which is presented on figure 8 as a compression between the 2. The beta-TCP scaffold withstands 500 kilopascals of compressive stress, which is about 2,500% higher than the pristine scaffold. Finally, figure 9 shows the cell proliferation on gelatin and gelatin with beta-TCP scaffolds. The cell proliferation in the porous beta-TCP scaffold is much more present than the standalone gelatin scaffolds. In conclusion, the performance of gelatin with beta-TCP scaffolds were far superior to pristine gelatin scaffolds in each analysis. Gelatin with beta-TCP appears to be a promising scaffold material for bone tissue engineering. Thank you for your time to listen to this presentation. Goodbye.